Thanks, Joey. All right, good evening. Thank you all for being here this evening. Welcome to the Lunar Planetary Institute. My name is Andy Shaner. I am the the public engagement lead here at LPI, and we're very pleased to have our speaker with us this evening. But just a few things before we get to that. Let you know if we have any teachers here. We have some 1 hour professional development certificates up on the front desk, so make sure you stop by and grab one of those before you leave. And then following afterwards, we'll have a reception in the lobby, and you're all more than welcome to join us for that as well. We'll do a Q&A at the end, and we'll go over more how we're going to handle that when we get to that point. So thank you for being here. Now I'd like to have LPI scientist Dr. Paul Spudis come up and introduce our speaker.
Thanks, Andy. Thank you. It's my honor to introduce Dr. Harrison Schmitt tonight. 45 years ago, we went to the moon for the last time. And I was just asking Jack about what the launch date was, and it was supposed to be on the 6th of December, 1972. But because they had a slight launch delay, it ended up being the 7th of December, Cape time. 1972, and that was almost 45 years ago. And two men went to the moon for the last time and hasn't been back since. And I think that's an appalling situation, but hopefully it'll be corrected in the near future. I am very pleased that Jack is with us tonight. By profession, he's a geologist who started his career at the U.S. Geological Survey. He applied to the very first group of the scientist astronauts that NASA advertised, and was selected in 1965. He learned how to fly jets, props, all kinds of aircraft, and was very instrumental in instructing and tutoring the early Apollo astronauts in geology and helping them to learn how to collect samples, how to recognize the right samples, and how to comprehensively sample a site. He was selected for the Apollo 17 crew after the flight of Apollo 15, which he was the backup limb pilot. He was the lunar module pilot on Apollo 17, which flew to the Taurus Littrow Valley, which you're going to hear a lot about tonight. And when he came back, he worked at NASA for a few more years and was elected to the United States Senate and served a term as the senator from New Mexico. And since then, he has been a researcher, a scientist, and a speaker on a variety of areas of public interest and importance. So I'd like you all to help me welcome Dr. Harrison Schmitt to the LPI.
Appreciate that very much. It is always a pleasure to come back to the LPI because I was at a time when the LPI didn't exist, and we're coming close to 50 years now for this vulnerable institution, and I hope it has at least another 50 years, and then we get a whole bunch of new lunar samples for you all to think about. The original LPI, as some of you remember, used to meet in the old Rice Mansion over here, and it was a beautiful place to meet. We didn't realize how few we were who were interested in lunar science at the time, and planetary didn't even enter the lexicon yet at that time. But what we're going to do today is take a little voyage to the moon fairly quickly, and then talks about what, at least in my perspective, are some of the major discoveries that came out of the Apollo 17 mission. I love this picture because it takes so many things in one glance, and actually in one glance, both of the astronauts are in this picture. If you look carefully, you'll see what has recently been termed a stagehand reflected in my my visor. And I wish Gene Cernan was around so I could tell him that he's now a stagehand. But the technology that was required for Apollo is illustrated by the human being in a spacesuit, two human beings in spacesuits. The science is represented by the South Massif behind me in this picture. The relationship of that science to the science of the Earth is demonstrated by the Earth above the flag, and of course the flag itself is representative of the American taxpayer that made all of this possible. Just so we don't forget, Apollo was a Cold War program. It was not a science program. And it is to the great credit of many scientists outside NASA, inside NASA, and engineers such as George Low and Sam Phillips that made it possible for science to benefit greatly from our excursions to the moon. All of this was enabled primarily by the existence of the Saturn V launch vehicle. You see that from a technical point of view, enabled by the Saturn V. This picture near this vehicle assembly building, that rocket is 364 feet high, fully fueled, weighed 6.8 million pounds. The thrust of the 5 F1 engines in the first stage totaled about 7.5 million pounds, just the largest rocket yet to be used in the access to space. A remarkably robust system that worked every time we asked it to. Now, the building that you see there on the right, the vehicle assembly building at the time, was the largest enclosed space on the planet. Since been eclipsed by, first I think by the Mall of America, and now, if I understand correctly, by a 787 assembly building in South Carolina. But still a very big building, and its size is relative size is sort of illustrated by the red fire truck down there in the lower right of the picture. That's a big fire truck, believe me. The launch of Apollo 17 shown here was, as Paul indicated, was delayed 2 hours and 40 minutes because the computer thought that it had not pressurized the LOX tank in the S4B, the third stage. It turns out it had not sent a signal to pressurize it, and that's what it was looking at when it went through its final checks at 30 seconds. It thought it had not pressurized the tank, so it stopped the launch. The last, I think, 8 minutes of the launch was pretty much all computerized. But you had real people in the Launch Control Center that when they saw that tank the computer had not pressurized the tank, the launch controller just reached up and pressurized the tank with a button. Well, the computer didn't know that. So we were ready to go, it's just the computer wasn't ready to go. If you look carefully on the left side of this picture, the rocket, you see some small spots. Well, they're not really small. They're big chunks of frost that are coming off the cold exterior of the Saturn V. By sitting in the Florida humidity for 2 hours and 40 minutes and even longer pre-launch, since fueling, we collected quite a bit of frost. Now, fortunately, the first stage engines, those F5, F1 engines, created a very heavy, low-frequency vibration, and that got rid of almost all the ice, with the exception of a little bit of ice that we saw later on the way to the moon that had come off the third stage of the rocket. The spacecraft that we're going to use on the upper right is the Command and Service Module, primarily the responsibility of the late Ron Evans, who we'll talk about a little bit more later with respect to the actual landing. But and also the Lunar Module Challenger in the lower right, which was enclosed by these 4 panels in the upper stage, just above the third stage of the rocket. They were extremely reliable for us and for the entire program. It was just the whole program was a remarkable feat of engineering. And it was unfortunate that, as I think even Paul would agree, that we had not had the perspective as a country, and certainly in the leadership of the time, from the Johnson administration forward, to keep this robust system alive so it could, in fact, do many other things for us and be upgraded and refurbished in many different ways. It would have been a very different world, I think, had the Saturn V still and its successors been available to us. Now, this picture is one of a very large number of pictures of the Earth that I began to take actually right after, just before the translunar injection burn that put us on a course to the moon at 25,000 miles an hour. It is the so-called blue marble photograph. And the reason this was taken and all these other pictures taken is that not that I suddenly realized, oh, there's a great picture that'll stimulate the environmental movement, so I think I'll take it. But because I had grown up with a father who was very interested in meteorology. And we spent a great deal of my childhood trying to forecast weather patterns in the southwestern United States, and particularly around Silver City, New Mexico. And so I thought that because of this interest in meteorology, that flying cross-country flights just reinforced at 40,000 feet, I thought that the thing to do for as much as I could for 3 days to the moon was to look at the weather patterns of the southern hemisphere that you see here and try to make forecasts of what they would look like 24 hours later, because in our lunar reference trajectory, that we were going to see the Earth rotate beneath us every 24 hours. And so I even launched with the latest satellite, very black and white satellite pictures in my suit pocket, so I would have at least a day lead on making those forecasts. And this photograph actually was just part of that sequence of documenting what the weather patterns were to go with my descriptions that filled several hundred pages of transcript now. It was a great opportunity, and I enjoyed it very much. And in this picture, you can see that we've got a nice cyclone going shore on India here. I'm sure the Indians and Pakistanis there did not care for that cyclone. But you see how symmetrical these anticyclone patterns in the southern hemisphere are, with the fronts coming out of Antarctica. The whole continent of Africa is visible, the Mediterranean up here, and if you're paying attention, you'll realize that's not really a full Earth. We're just too close to it to see a full Earth, but it's not a bad picture. As I understand, it's still the most requested picture from the NASA archives, and I'm very proud of it. Now, where were we going on the moon? Well, Apollo 17 was going to land in a relatively narrow mountain valley that cuts through the ring of mountains surrounding a very large impact basin, 740 kilometers in diameter. That's called Serenitatis. Relative to the Apollo 11 landing site, that's approximately 600 kilometers north and a little east of that site, of where Neil Armstrong landed in July of 1969. The valley itself, Taurus Littrow, in this picture is about 50 kilometers long from lower left to upper right. It's at its narrowest point, and indeed about where we were landing, it's about 7 kilometers wide. When it was first being considered as a landing site, the so-called error ellipse of landing was too big to get into the site. It meant that, and for those of you who are into error ellipses, this was a 3 sigma ellipse, very conservative ellipse. And the right-hand part of that ellipse actually came up onto the North Massif here. So it didn't look like we were going to go to Taurus Littrow, and they were looking at other sites, all of which, believe me, any place you go on the moon is going to be interesting. This one particularly interesting because of the three-dimensional aspect of it. This mountain is 7,000 feet high, 2,100 meters. So it's deep into the Grand Canyon as a valley. So it's a good one. And over here it's about 1,600 meters, as I recall. What Ron Evans called his Spaceship America is there. And what Ron is doing at this point, he's out ahead of us. This is the orbit prior to our actual landing. This picture was taken. Ron is taking landmark sightings, small craters in the landing area, the position of which we knew relative to the center mass of the moon, based on other photography, particularly lunar orbiter photography. And with that knowledge, he and the ground computers, he'd ship the data back to the ground, they'd process it, they would update the state vectors, the position and velocity information for the 2 spacecraft, and give us that just as we came around again for the landing sequence. And that was a little dicey. We had to get that state vector in just a few minutes relative to into our computer, our guidance system. And so that that ellipse then shrank down to about 1 kilometer. And that's what made it possible to land here, was that very innovative way of getting that, that new position and velocity information into our computer. But thanks to Ron, he did these outstanding landmark sightings, a technique actually that Jim Lovell and I developed for Apollo 8. It was first tested out on for that mission. Very important part of precise landing on the moon. Now, just to show you that there is some documentation of us landing in the Valley of Schmitt, this is a picture taken by a photograph taken by the Lunar Reconnaissance Orbiter that is still functioning and giving us a great information around the moon today. And there is the descent stage of the Challenger, our lunar module. The lunar rover is parked over here, and you can see those tracks going out to it. And this is my very sinuous path carrying the ALSEP, the Lunar Science Experiment Package, out to a site where we deployed it. When I saw this picture, I said, God, why did I walk so far? I knew I had to be 100 meters away from the lunar module. That was the constraint. But this is 180 meters, and my arms were really getting fatigued by the time I got out there. This probably was a little better site right here, but I walked right across it and ended up over here. I finally just said, oh, heck, let's just deploy the thing. And now, one other thing in this picture, in the even higher resolution images of this, there's a shadow right there that is the shadow of the American flag. And I don't know about my other colleagues, but I never talked about the American flag still flying on the moon. I never mentioned it one way or the other, because I thought that nylon it was made of would have deteriorated in the ultraviolet light by this time. Well, it turns out it hasn't. And so at all 6 sites, the flag is still casting a shadow. What kind of condition it is, we don't know, but it's great that it's there after 45 years. It's just tremendous. And I understand that DuPont is searching their archives to try to find the formula for that for that particular batch of nylon. Whether they found it yet or not, I don't know. The first view I had at the lunar surface after landing is this one out the right-hand window. The base of those mountains are about 3.5 miles away, but it's a very typical Mare surface. The only thing atypical about it, and go back to this, is that the descent engine has winnowed away the fine particles right around where we landed. And those fine particles are darker than the coarse particles. And so that's why it looks like there's a light area around the lunar module. And it's the reason you can see my tracks and the rover tracks is because of that light. And then when you walk, you stir up the darker material underneath. You get very far away from the lunar module, and you play, pardon the expression, hell, trying to find our tracks. Now, people have found some of them in some places, but it's not easy. It's not easy. It's just because the surface has been modified by our landing. The shiny object in the foreground is one of the 16 reaction control system thrusters that helped us guide the spacecraft in flight. They had about a 50-pound thrust, restartable. Not much, but I mention that because then the total spectrum goes from 50 pounds to 1.5 million pounds in the first stage of the Saturn V engines. And we had several different propulsion systems in between. So again, the technology development in a very short period of time was truly remarkable. Again, about 2 EVAs later, 2 extravehicular excursions later, I took this picture, roughly the same view, and it shows you how we have stirred up the debris layer, the regolith, that covers most of the moon. Initially, it has very high bearing strength. You don't sink in very far at all, but as you work it, It's like damp beach sand, playing volleyball on damp beach sand. It gradually gets worked up until it gets deeper and deeper, which is a challenge for those of you who end up going to the moon one of these days. You're going to have to figure out how in high traffic areas to stabilize that surface, because it's just going to get deeper and deeper on you. I think there are ways to do that, but it'll be a bit of a challenge. Now, what it takes to really be on the moon, at least for 3 days, is what you see here, and to actually explore it. The lunar module there in the background is your camp. We spent our rest periods there. The total time on the surface was about 75 hours. The suit of the astronaut, the spacesuit, yours truly there posing, is another spacecraft, really. It has all the components of a spacecraft: an environmental control system to keep you cool and breathing, it protects you in many ways, has emergency systems in it. Very nice. And the only thing that is a little abnormal is that you have to supply the mobility of that suit. There are no reaction control thrusters to move you around. Not yet. Someday they probably will be. And then in the background, under the flag there, you see the Lunar Rover, which was our transportation on the surface. We eventually drove that about 32 kilometers total. The farthest we got from the spacecraft on EVA-2 was about 7 kilometers. And believe me, we were out of sight. And there was some concern about walk back, and we may talk about that a little bit later. That was the constraint on how far we could go. And so you'd start out an EVA, like EVA-2, going to the farthest point that would allow you time to walk back if the rover got stuck. Is the rover going to get stuck? No, the rover's not going to get stuck. But again, a very conservative program. In fact, it didn't weigh enough to get stuck, because if it did, you'd just get out, lift it up, and move it. I mean, it's only 450 pounds on Earth. Divide by 6, and you know what it was on the moon. So, but, you humor the risk management people in NASA, and that was over-managed risk. And then, of course, you need a national support, such as we had demonstrated here by the flag again. Now, that spacesuit I mentioned, that is the NASA, of course, had to call it an EMU rather than a spacesuit. EMU stands for what? Extravehicular Mobility Unit. I'm surprised I remembered that. And here you see me operating. Now, my weight and the suit and backpack total about 370 pounds, Earth pounds. Again, you divide by 6, and so you can see that although the mass was staying the same, that the moving it around was not particularly difficult. The only real physically difficult part of working was using the gloves. And using those pressure gloves, 3.7 pounds per square inch in the suit, every time you move it, it's like squeezing a tennis ball. And so that worked these forearm muscles a great deal. And knowing what I know now and knowing what I found out then, we did not do nearly enough physical training for those forearms, even though we did it quite a lot compared to what the shuttle astronauts have done in order to assemble the International Space Station. We were pikers. And having a much better training program for those, a physical training program, would have been a great assistance in this mission. What I'm doing here is taking a sample. We call it the rake sample, but actually it's a sieve. The tines on this sieve are about a centimeter apart, and so the very fine debris would go through, and you would collect the coarser fragments from a particular area. In this particular sample, well, and the logic behind this is that if you get the smaller fragments, you're going to collect a lot of exotic fragments from all over the moon, okay? Because that's the way the moon changes itself, is through impacts. Well, in this particular sample, we got none. It was all basalt fragments from just the local area, and it turns out it is a very useful sample for understanding the shall we say, the science of crystallization of these Mare basalts. It's the only sample of the kind that I'm aware that we have. That I don't begrudge that at all, but we didn't get any exotic fragments in this sample. We got them in other sieve or rake samples. You may recall the episode of a certain commander on this mission hooking a hammer handle underneath our fender. The fender was really a dust flap. It kept dust from following a forward rooster tail and raining down on the astronauts and the rover. This shows you the job that was the fix that was put together overnight in the Mission Control Center. I'd been involved in many of those myself, and I knew exactly what was going on. They got everything that we had in the cabin available to us, put it on a table, and stood there and stared at it and says, how do we create a new fender out of this? Well, there you see, unused photo maps, gray duct tape, and 2 clamps that were light clamps that we never used in the spacecraft anyway. And it worked very well. In fact, it's in the Smithsonian in Washington, if you ever want to go see it. We brought that back and of course became honorary members of several automotive repair societies. But that forward rooster tail was something you didn't want to have. Now, over at Shorty Crater is where we found the orange soil, and if you look carefully, you'll even see some orange color in this picture, a little more down there. That orange soil, I just walked up to that boulder, you see, because every time a geologist sees a boulder, he's going to go sample it, right? Well, as I walk up there, another thing geologists usually do is they're looking at their feet. And as I got close to it, I noticed that I was scuffing up something that looked a little orange. And my first comment was, wait a minute, where's the rover? People always ask me, why in the world did you say that? I said, because at another site earlier, I had almost sampled an orange reflection off the rover. Those fenders are orange, and it was reflecting light down on the ground, and I was there with my scoop ready to sample it before I realized I was sampling a reflection. And so that's the reason I said that. But it turned out to be about a meter by 3 meter exposure of volcanic ash. We didn't know it at the time, found that out later, but a very, very fine-grained beads, glass beads, the orange. Underneath it, we discovered by putting a core tube through it, 70-centimeter core tube down through it, most of the deposit was black, and it was partially devitrified beads of the orange glass. It had turned black. I'm sure this is nerdy stuff, but because the ratio of iron to titanium changed when it devitrified, and so the glass became clear, but the minerals were dark. Yeah, right. So I knew you'd be excited about that. Anyway, this sampling of pyroclastic deposits has become very important to understanding a broad number of questions about some of the materials on the moon and about the interior of the moon, because only a few years ago, workers looking at inside the beads, these beads of glass, at some olivine peridot crystals in the glass, they found water in the olivine, indigenous lunar water. So that was new stuff. But it was 40 years after we collected the sample before the technology was capable of making that discovery. And that's why the lunar samples are a gift that keeps on giving. As technology advances and ideas advance and interpretations advance, we're learning stuff all the time. There's a community, there's a vast community of lunar scientists that I don't know how they're being supported. Maybe Paul does. But it just keeps going. And the Lunar and Planetary Science Conference every year has many sessions on lunar research, and it's just a delight to see, particularly when you continue to try to understand the geology of your landing site. One of the biggest boulder and we knew this was there. We could even see this boulder on the Apollo 15 relatively low resolution photographs that we had to plan the mission. And so it became an obvious place to go to see this huge boulder. And when we got there, it was clear that it had rolled down the mountain and it left a boulder track, so we know exactly where it came from, and it gave us new insights into how do you sample these mountain slopes. Well, you go look for boulder tracks and track them up to where they came from and get a variety. And we didn't know it at the time, but at Station 7, the next station in this last excursion on the moon, we sampled another boulder, and it had a boulder track, but we didn't know that until we got the LRO photography. And again, technology advanced, gave us new information. So we actually sampled 2 parts of the North Massif, the north side of the valley, with these boulders, and really is the way I think we'll do an awful lot of future sampling on the moon. The lunar module now is off underneath that area, and you see that light-colored spot under the arrow. That's, again, what I mentioned earlier, the winnowed-away spot where the lunar module is. It's about 3 miles away. This is that boulder from another view, and this view actually shows you that the part of the boulder has a whole bunch of holes in it. We call that vesicular, and they're big vesicles. Some of them are 6 centimeters or more in diameter. They're just huge things. And that boulder and that material actually has intruded the material in the rest of the boulder. Now, back in the spacecraft, after the 3rd EVA, I think I'm starting to look a little bit tired here. The suit is certainly looking tired, and that's an issue for you future engineers, is how do we build a suit that you can use more than 3 cycles? Actually, the suit was qualified for 6 cycles, 6 days of use. But when we go back to the moon to stay, we're going to have to figure that out. You can't keep taking a whole bunch of suits up there. You're going to have to eventually refurbish, but you'd like for them to last a while. So my understanding is my suit is the suit of choice for trying to figure out what we did in Apollo. And so there's probably all sorts of holes in it now, people cutting chunks out of it. If you're, you can't do this, I probably ordinarily, but I went to a warehouse, Smithsonian warehouse, a few years ago to see my suit. And they took me into the warehouse, and we went inside this big refrigerated room, and they opened up doors and pulled these suits out on gurneys. Now that's weird. And particularly when your name is still there on the Oh boy. Now I'm a little happier and I'm in my underwear. You know, we call that, again, NASA couldn't call that underwear. It had to be a constant wear garment. CMG, or CWG, there you go. Well, we left the moon after that 75 hours. This is not a very good picture. It's taken off a TV set. Cernan tried to get me to go out and take a really good picture of liftoff. We'll leave that to some future somebody in the audience maybe. We'll take a picture of a liftoff on the moon. The upper half of the Challenger, the ascent stage, is rendezvousing here with Ron Evans again. Very active rendezvous. We gotten very cocky by this time, and we actually did a direct rendezvous. We didn't even do a full orbit before we had rendezvoused. We left the moon and caught up with Ron on the way up, and we were there. We were just cocky. we knew how to do it, you know. And I mean, why spend all that time going around and around the moon rendezvousing when you can do it this way? It worked very well. And this, I just enjoy showing you this picture. I consider it's the best entry into the Earth Rising Over the Moon sweepstakes, even though it never made it to a stamp. And splashdown near Samoa, excuse me, occurred within 1 minute of the planned splashdown time, even though we left the Earth a day, 2 hours and 40 minutes late. They figured out how to make up all that time, and we were there. And then there's the old Ticonderoga. Anybody here serve on the Ticonderoga? No? Every once in a while I run into people that have. I go to their reunions once in a while. It's no longer afloat. In fact, it's been made into razor blades or something, probably. And the Navy UDT team, which are now known as SEALs, instead of underwater demolition teams, were in the water very quickly, getting us set up to go up into the helicopter. Now, a little detective story here. You can actually, just from looking at their heads, tell which astronauts are which. This has to be Ron Evans because he's bald. And he was, I think, bald at birth, probably. And Gene Cernan is just starting to get gray, not nearly dark, so this must be me with a black head of hair at that time. That really culminated a wonderful opportunity for me and a great privilege to take that trip and to not only practice my profession on the moon, but to be part of a tremendous piece of American history. Now, let's talk about a few what the discoveries are. We've already looked at where we're. This is again, a lunar reconnaissance orbiter image that shows the various numbered stations that we visited and explored in varying degrees of detail. The major features, of course, are the North Massif, South Massif, an avalanche of debris off the South Massif, a fault scarp right here that goes across. This is actually almost certainly a thrust fault. That is, the rocks have moved over each other like this, and with about a 500, it looks like about a 500-meter throw, which is a major fault, and it may well be that fault is what triggered this avalanche. We're still playing with that hypothesis, but it looks like a pretty good one. In fact, it looks like you may have had two faulting episodes, because there's an older avalanche, darker here, that's partially buried by the newer one. And we even have samples from both the new and the old avalanche, because we had this little device called a Rover sampler, which actually was also called the Dixie Cup sampler, because it was on a rod, and you could just reach down and get a sample from without getting off the rover. And we got a lot of those samples, which are turning out to be very interesting in aggregate. The chances are that avalanche has been triggered by faulting rather than by an impact somewhere else on the moon. Now, the most interesting boulder is the one that's now probably the least studied boulder. This was at Station 2 over at the base of the South Massif, called Boulder 1. And I'm not going to go through all of these, but I'll just show you that it's a very complex boulder. We've had age dates on all sorts of parts of this, but these are now these are 40 years old, at least, a little bit more. John Wood from the Smithsonian Astrophysical Laboratory at Harvard led a consortium to study it, and these are dates that basically came out of that consortium. Dave Kring and I and others have been, and Noah Petro and other workers have been thinking about how do we revisit this consortium with modern technology and see what really this boulder has to tell us, because it's unique. All the other boulders look pretty much the same. They're different in many ways, but still they are nothing like this, have none of this complexity. So that's going to be an exciting job for the future, is to try to really take the four big samples that I was able to get off this in several different places up this boulder, and really work with those. I had a boulder also at Station 2. This was Boulder 3. I was running by it, and I noticed this light-colored fragment here. This now has been sampled. We chipped some stuff off of this when this picture was taken. By the way, that brownish patina that you see here, that's glass. That's that's impact glass. It's a glass patina. It's very thin. You can see through it, as obviously you can see things through it, but it's from micrometeorite impacts, just melting glass and putting it, spreading it around on a rock. Now, occasionally you'll get another impact in the glass, like right there probably, that cleans some of it off. But generally you get this patina of glass on all surfaces that are exposed. Anyway, this sample has turned out to be very interesting in that it has an isotopic composition and some mineral textures in it that strongly suggests to me, at least, that it came from the deep mantle of the moon, and leads you to start to think, how could that have happened? How could it come from, say, 500 kilometers down in the moon? And that leads you to think about a basin called Procolarum off to the west that is 3,200 kilometers in diameter, and that might be the kind of an impact that would cause the moon's mantle to overturn, and actually over geologic time, maybe a few tens of millions of years, bring these mantle samples up closer to the surface, where then they could be sampled by other large impacts. So I include that as a major discovery right now. A lot more has to be done. There is another sample from Apollo 17. It's called, from Station 6. It's out of that Reich sample at Station 6. It's a tractolite that 76525, for those of you who like numbers. And it has an even better set of mineral textures than does even this dunite. This rock is almost all olivine or peridot. So that's an exciting new area that we're working. And as I mentioned, did this big basin, 3,200 kilometers, to trigger the overturn that brought these close enough to the surface to be sampled by other impacts. The valley itself is probably a fault-bounded Graben. That's a term, German term, that we use for faults that we call normal faults, where they're just sliding in response to gravity or some other stresses, but they're normal. It's what you would expect a fault to be, rather than a thrust fault that is riding over other things. Now some of those, it's a complex Graben. It's if that's indeed what it is, and there's no reason to think it isn't. And these are just some of the possible directions of the faults that formed it. And it is generally thought to be of the same age as the basin that we landed next to, the Serenitatis Basin. Now we're going to talk about these boulder tracks a little bit. I've tried to identify with arrows some of the tracks, and I hope you can see. It's that image on the screen, at least from where I am. Do you see the tracks? The image is a little bit darkened by this angle, and the tracks. The boulder at Station 6 down at the bottom there, and Station 2 come from different parts of the moon, of the slope of the massif, and there's about a 500-meter vertical separation between those two samples. And it's now the analysis of those samples, more updated than the Boulder 1 that I mentioned earlier, is starting to give us some new ideas about the age of of some of the basins from where these boulders materials may have come from. Now you can see the tracks that I'm talking about much more clearly, and actually there are probably about 10 tracks that I counted when I started to work on these pictures, just in this one image. This is that boulder again at Station 6 you've seen earlier. And I mentioned that there was a contact zone between the tan gray rocks that have holes in them, vesicles, and this blue gray material here that has some vesicles, but nothing to the degree that this has. And there is evidence of melting in this contact metamorphic zone which is strongly suggests that this material, however it was deposited on the older material, was hot enough to actually melt, partially melt the material in the contact zone. These rocks, for ages, these are on the order of 3.9 billion years old, based on argon dating, isotope dating. Now, Station 7 had much the same appearance. There's a contact between highly vesicular rocks and some blue-gray rocks. But in this case, the ages are very different. They're down in the 3.8, 100 million years plus or minus difference in age. So that this boulder coming from higher up on the North Massif slope, as you might expect, turns out to apparently be younger within the statistics, younger. So that's been very exciting new information about what might be in that be forming that North Massif slope. And so what the current interpretation I have is that we have ejecta from one basin to the south east, called Crisium, at about 3.93 billion years, and the Serenitatis basin being about 3.83 above that. Now, there is general agreement that above that is material from the Imbrium basin, which is a very large basin over to the west. That basin is about 1,000 kilometers in diameter, and the sculptured hills appear to be ejecta from that basin. Now, what about these sculptured hills? It's a physiographic unit. That's a term that was applied by the mappers, USGS and other mappers. And I've outlined where it is exposed. It's not only exposed up on top of the North Massif and to the east of that massif, but some of the hills in the valley itself may appear from other data to also be related to these sculptured hills here. That data comes from an instrument that flew on the Indian satellite, you pronounce it? Chandrayaan. There you go. And it carried a mineralogical mapper, so-called M-cubed, and we had visited a part of the edge of the sculptured hills there at Station 8. This is North Massif. These are the sculptured hills, and the M-cubed false-colored images are being interpreted as showing different concentration of minerals in various places on the knobs of the sculptured hills. The knobs you can see in other lunar reconnaissance orbiter photographs that the knobs have concentrations of boulders on them. So they're giving pretty good signals to the M-cubed sensors. And just as down in the valley floor, the basalts are rich in clinopyroxene, particular calcium, magnesium, largely magnesium rich pyroxene. And so that sort of helps calibrate these sensors. The North Massif is plagioclase rich. Again, the blues tend to indicate plagioclase. That's a calcium aluminum silicate mineral, and then you have the reds are being interpreted as olivine rich, and the yellows as orthopyroxene rich. Now we've got. I hope that this data continues to be massaged and we get better and better resolution on it. But it's starting to give us a picture of what that North Massif might be and what ejecta from the Imbrium basin, at least in this particular place, might consist of. Now, one of the things that had bothered me for decades is what happened just before these lunar basalts erupted into the low areas of the front side of the moon, mostly, and we had I suddenly realized that I had a unique opportunity to look at this question. My thought was that the first thing that when you start to partially melt the mantle of the moon, the very first thing that's going to appear are volatiles or gases. And we know that there are gases in in that area because the basalts have holes in them, and those holes are caused by gases. And we see that on Earth all the time, and essentially almost all the basalts we see on the moon have these holes which used to have gases in them. We don't know what they are because they didn't alter anything. They didn't change anything. It just were there, and then they disappeared. So initially, gases would come up, and you'd have eruptions at the surface of these gases. Well, going through the crust of the moon, they would pick up fine-grained mineral debris. You would expect them to. And so you would have what we would call lithic or rock-rich volcanic eruptions at the surface of the moon before the lunar basalts ever started to fill low areas like the Valley of Taurus Littrow. Well, at Taurus Littrow, we have two places where you could test this. You have old regolith, old material, very old material, at least 3.8 or 9 billion-year-old debris that's coming off the North Massif, and you have young regolith over on the South Massif at Station 2, which is young because the avalanche cleaned it all off. So it's new in that case. It's been formed since the avalanche. And are they different? Well, it turns out they are. There's a bell-shaped fragment size distribution curve in the new regolith, as you would expect. Most regolith has that bell-shaped shape with a peak at 60 microns. And over on the North Massif, however, it's asymmetric distribution. The more fines, its peaks at 16 microns. So a very distinct fragment size distribution between the two. And it turns out there's also a very distinct mineral distribution where under this hypothesis you would expect to see a lot of mineral fragments. On the North Massif, that's exactly what you see, circled there in blue. And in contrast, over on the South Massif, where you have the young regolith, you have mostly fragments of breccia. And so I think maybe we finally have some concrete evidence of what happened before these dark areas of the moon actually formed and basalt started to fill basins elsewhere on the moon. Of course, we talked about Shorty and the pyroclastic material they found there. That's a relatively close-up picture of the orange soil. Underneath that is a lot of black soil, and the structure of that deposit looks like it's sort of an overturned fold that you see here. I'm not going to go into detail on why that appears to be the case, but because we have a core through it, we can get some of this kind of information. Now, but what I really want to focus on, this is what we call a stratigraphic section of that pyroclastic deposit, and we wouldn't have found it if it hadn't been protected by a ejecta blanket of regolith that covered it soon after it erupted. Otherwise, it would have been incorporated in the meteor redistribution of material as everything else was in the Valley of Taurus Littrow. But what really has started to interest me, and at the AGU meeting here in December, I'm going to, our next, week from now, I'm going to talk about a particular thing. This ISFEO ratio is called a maturity index. Most of the debris in the Valley of Taurus Littrow would have a maturity index between 40 and 80. What that is based on is that when micrometeorites hit a particular spot, they have a very high temperature at the point of impact, and it actually disassociates iron oxide. So you end up with little particles of iron. They're called nanophase iron particles in the glasses, and that accumulates over time, and it's one measure of the maturity of a regolith. Well, in this particular case, very low maturity. Now this stuff is 3.5 billion years old. It has exposure ages of on the order of 500 million years, and you wouldn't expect that. what it suggests is that at 3.5 billion years ago, there was a very low flux of these micrometeorites. The space was relatively clean. Nothing was happening. That is very interesting. If it almost certainly is true. And so why? What was going on there? Now there is a group of people in Italy, and they have developed what's called a NEAS model for activity in the outer solar system, and where Saturn and Jupiter do sort of a exchange dance, move around. Well, that kind of thing would seriously disrupt the asteroid belt, and would probably, when it happened, create a high flux of micrometeorites and macrometeorites as well. So this starts to put a constraint on how late that could have occurred. Almost certainly happened before 3.5 billion years ago, which is, I think, a pretty interesting way in which the moon is telling you something about the outer solar system. So, also we have opportunities for looking at the orientation of the lunar magnetic field. We're certain that there was a global magnetic field on the moon. Right now, all the instruments that we flew say it's zero. It's not there. There are old areas of magnetic fields, but nothing global. Well, when I was preparing to go to the moon, I knew that other guys had seen in small craters, these puddles of glass, impact glass. So I planned to sample one of those, and I did. And just in the last couple of years, we have gotten busy on that sample, oriented it, and now it's being looked at as a sample by Ben Weiss at MIT, as a way to see what the global magnetic field might have been just maybe 10,000 years ago, because that glass doesn't last very long. It gets destroyed by impacts. So it's a very young measurement of a very young magnetic field, if it's there. Now, there is magnetic intensity, paleomagnetic intensity in it, but what he's trying to do is see if there's a consistent or a believable orientation of that paleo field. And we have other opportunities to maybe do the same thing at Camelot Crater and some of the basalts. We can probably reorient those and make a measurement. That would give us a date something like 3.7 billion years ago, 3.74 maybe. And then there's one other opportunity for doing the same thing. So at least in 3 different parts of Paracelestro, we may get a story on the lunar, the history of the lunar global magnetic field. So that's just a very small sample of the kinds of information that can come out of both doing field work and integrating it with the isotopic and chemical and petrographic work that others have done in the last 45 years. And with that, if we have time, I'd like to take some questions.
Are we going to use the microphones? Oh, here comes Andy.
Oh, great. There we go. If you had a question, please raise your hand so overflow folks can hear you, and online as well. We'll take a couple in here, see if we have any overflow, and then come back.
Hello, Dr. Schmitt. Did you ever have an occasion to work with Gene Shoemaker with all the Apollo geology related stuff?
Well, I wouldn't be here if it weren't for Gene Shoemaker. I not only worked for him for a year in Flagstaff, Arizona, but when I was looking for a job after finishing my dissertation at Harvard, I couldn't find one. Not only was it there weren't any interesting jobs, there just weren't many jobs in geology. It's a periodic depression we have to go through, but I had met Gene Shoemaker in Menlo Park some years before, when I went out there at the invitation of a petrologist named Bob Coleman to look at some rocks in that in California that resembled to some degree the rocks I'd been working on in Norway for my doctorate. And he, when I went to his office, he said, "You ought to go down the hall and meet this fellow, Gene Shoemaker, who's mapping the moon." And so crazy stuff. So I went down there and met Gene and Danny Milton. Some of you know, probably remember Danny. He was working for him, very bright guy. And I said, "Anything Danny's interested in probably is interesting." And so I met him. And then 2 years or so later, when I couldn't find a job, I just wrote Gene a letter asking if he had any openings. And it turns out he wrote me a letter and they crossed in the mail. And so that's how I went to work for Gene. And when a few months after I arrived in Flagstaff, the announcement of opportunity for scientist astronauts appeared on the bulletin board. And I thought about 10 seconds and said, well, I probably ought to try to do that. If somebody goes to the moon and I had a chance to at least volunteer, I'd probably regret it. But the first thing I had to do was talk to Gene because I'd committed, to work for him. And he said he never hesitated because Gene wanted to go to the moon. He really did. And unfortunately, he contracted Addison's disease, and that was not going to happen. He was 2 years beyond the age limit, but I think NASA would have made an exception for Gene. But that, since that didn't happen, I owe Gene a great deal. He actually chaired the selection committee too. Yeah, Harry Hess, his mentor at Princeton, asked him to chair the selection. He claims that he reclused himself, but somehow or another, several USGS candidates appeared on the final 16 that were evaluated for physical and other things. Some of you might be interested. There were 1,400 applicants in that first round of scientist astronaut. A few years later, there were 18,000. But I mean, that first round, I thought I was low. I thought that was low. I expected more than that. But nevertheless, out of that 1,400, 400 were evaluated after they had submitted their FAA physicals, the first requirement, and that took out all but 400. The Academy committee evaluated those and then asked 80 to submit some additional materials besides the transcripts and everything they had already submitted. And from that 80, they recommended 16 to go to Brooks Air Force Base for 8-day physical. If you've ever had a physical that took 8 days, I don't recommend it. It was something else. But and from that, 6 of us then, all 16 were interviewed by NASA, and 6 of us were selected. But I guess I should say, fortunately, I was the only geologist. But there should have been more. Gene and I debated that through the years before his untimely death, of whether they shouldn't have sent more candidates to NASA for that particular selection. But nevertheless, it didn't happen. Yes. Well, go ahead.
Yes, sorry. Last summer, I got to visit a company near Princeton that's working on a fusion rocket under an advanced concept contract with NASA using helium-3. Could you talk some on the discovery of helium-3 in the samples? And are you still working with the University of Wisconsin on some of these concepts of mining helium-3?
The Wisconsin group, which sort of initiated that whole idea, yes, is still active. The funding is not abundant for this particular area of activity, but the moon hasn't changed. I mean, it does represent a source of helium-3. Helium-3 produced in the sun is embedded in the lunar regolith, and probably reaches sort of a steady state there. Right now, the concentration in my analysis is about 20 parts per billion helium-3 in the regolith. That doesn't sound like very much, but 100 kilograms of helium-3 would power a fusion reactor that would supply a city, say, the size of Dallas for about a year. A tremendous amount of energy in this isotope. And the ideal reason why it's of interest, or the primary reason why it's of interest, is that it doesn't produce any neutrons when it's fused with itself. When fused to deuterium, it does produce a few neutrons, low energy neutrons, not a serious issue. But fused with itself, there are no neutrons. And neutrons are the bad actors. Those of you who know nuclear physics know they're really bad actors. And any fusion or fission process that produces neutrons causes all sorts of engineering difficulties. Whereas we think helium-3, ultimately helium-3 fusion reactors would represent a much simpler, low capital intensive way of producing power, but you still have to get it from the moon. There are not supplies here on Earth other than those produced by the decay of tritium. Tritium is used in nuclear weapons. It's made in reactors. It decays with about a 13-year half-life to helium-3, and so there is helium-3 on Earth, but it's primarily from that source. Unfortunately, the Homeland Security Department has corralled most of the helium-3 because it also captures neutrons and gives off a gamma ray in response to that capture, and that means it can be used in neutron detectors at the border to see that fissional material isn't coming in. At any rate, no, I think it's still a very important area. I have heard about the Princeton group. I do not know any details about it at all, other than I've heard about it. I've been intending to talk with my good friend Will Happer, who ought to be the next science advisor, as a matter of fact, but Will Happer at Princeton about it and find out what's going on. There is a Paul Allen funded effort called Tri-Alpha, which has recently, about a year ago, become more public. They put out a release. They're not working with helium-3. They're trying to develop a system to fuse protons with boron-11, p-boron-11 cycle. It's a cycle. It does produce some neutrons, it actually goes through several steps. But the technology that they're developing at Tri-Alpha is consistent with also using helium-3. They just don't believe you're ever going to get helium-3 from the moon. So they're working on a different system. But that's the p-boron-11 as well as helium-3 are far preferable to what has been going on for decades in fusion development. Tritium-deuterium fusion is a non-starter commercially. It's just not going to make it. It produces 5 times the neutrons that a fission reactor produces, and you can't recycle it because those neutrons then create radioactive waste in the walls of the reactor, and that's not going to do you any good at all. So at least fission waste you can recycle if Jimmy Carter hadn't stopped it, but that's a different point. Any other questions?
Do we have any questions from the overflow room?
I'm sorry?
I'm just checking to see if we have any overflow room.
Oh.
No, we don't have any questions from the overflow.
Right.
Hi, Dr. Schmitt. I was just wondering what your
Oh, here we go.
what was your absolute favorite memory from your time there, and what was your biggest challenge?
The favorite memory is the mission. I think Drew might agree. I mean, the whole thing is just an immense charge, and from all the way through, from training on through the mission itself, it's really exciting. For me, it was exciting. Something I had, of course, never expected to do until that announcement appeared on the bulletin board. And even then, I didn't expect to do it. I think the biggest challenge for me was as a young cadet pilot who's 10 years older than all other cadet pilots, is breaking some habit patterns and learning to fly instruments in a jet aircraft. I would say that challenged me a great deal, and I finally mastered it. I think I was a pretty good instrument pilot, but it was not easy. at least for me in science, I tend to focus on something and then I move over here and focus on it and then I go over here and move it. You can't do that when you're flying instruments. You got to keep a scan going. And learning to do that scan may sound very simple, but learning and maintaining the proficiency to scan your instruments and make small corrections continuously, that was something I had to really learn. And if I had been 18 years old, probably no sweat. But when you're 28 years old and 29 years old, it's something else. But I would say that was the biggest challenge for me.
When we get back to the moon, what are the top priorities for geologists, in your opinion? What would you say the things that they should concentrate on are?
I talked about that in a seminar yesterday. I think there's some major contributions that we should focus on. One is to really start to pin down the history of the very early Earth. The moon is our record. The moon's our library. What the moon experienced in its first billion years is really what the Earth experienced in its first billion years, with one major exception, and that is during that first billion years, complex molecules were getting organized here on Earth, in spite of the fact it was a period of extraordinary violence, huge impact. I'm talking continental scale basins were forming here on Earth as they were on the moon. And that is a real interesting conundrum. Conundrum. I've been a geologist too long. And that is that how did these molecules get organized in an environment as violent as what the Earth was experiencing? And it's not just a surface environment, it's an environment at depth as well that was getting pounded. So that's something that I find very exciting to think about now. But pinning down that billion years in more detail, was it a continuous time of impact? Did it come in pulses? Or what? It really starts to define what we call the Hadean on Earth, an eon before the Precambrian, really, or the Archean, that is very mysterious to us. Now, one thing we have found in recent years, through the great work of people like John Valley at Wisconsin and other places, is that we now know that there are the mineral zircon was being formed as much as 4.4 billion years ago, and we have sampled those zircons in what are called detrital rocks, primarily in Australia right now, but there's some that are not quite that old in Canada as well. So those are the first real hints of material that may be related to that early Hadean period. In fact, I'm sure they are. I think the analyses are there's no reason to question those 4.4 billion year old analyses on zircons. Zircons are very, next to diamond, they're probably the most resistant mineral that we have on Earth. And so I think there are a lot of people now really trying to work to expand that knowledge, at least through zircons, of what was happening on that in that early period called the Hadean. There are quite a number of other things that would be worth looking at, but that thinking of your geologic plan of exploration to at least get more answers to that question. We have some now. We know it exists. We know that record is there on the moon, and we know some of the points in that record, but it's not very well defined. I'm sorry, I'd point to everybody, but
I read a study paper at one point. I think you might have been involved with. It's a lunar dust problem from liability to asset, and the thing that it actually brings up is we're talking about the potential for settlements on the moon and what's needed to actually fulfill that potential in terms of you take the lunar dust and what you were just describing in terms of the resources that are there. My question is if you can discuss more on the resources that would be needed for exporting various commodities and resources from the moon to such as oxygen, water, so forth, to low Earth orbit, to the Earth, in terms of travel back and forth. I know this is something that was discussed in terms of our International Space Station, how you can actually develop a colony on the moon, but make sure that you actually have the resources in terms of the commodities that can be transported back to Earth and back to low Earth orbit. So can you speak on that?
Sure. The book I wrote called Return to the Moon, published about 10, 12 years ago by Springer, is looking at the economics of those resources, but it's the economics of resources that are byproducts of the real payoff for a lunar settlement, and that's helium-3. But the byproducts in the dust that you mentioned, and that paper was, of course, by the late Larry Taylor, and I was privileged to work with him on it. That dust, in fact, about half of the lunar regolith is less than 100 microns in diameter. It is dust, but that is where most of your lunar resources are located. They're not located in the pieces of rock yet. Someday they will be. But the volatile resources of the moon, which is what we're interested in initially, namely hydrogen, oxygen, nitrogen, carbon, and water. You can make water anywhere on the moon. If you heat the regolith to about 700 degrees, you'll start about a third of the hydrogen. It looks like it'll come off as water. Now, we also know there's water ice in the permanently shadowed areas, or appears to be. There's hydrogen in the permanently shadowed areas, and very probably some of that is water. How old that water is another question, and where its source is another question, and how you mine and access a resource that's at 40 Kelvin temperature. Those are all questions. They all have answers, I'm sure, but they're real issues. So there are many options, I think, for a lunar settlement to develop an economy that will support itself. Helium-3 is clearly an exportable resource to Earth if you can develop the reactors to use it. But the other consumables that will be of use in space, the ones I listed, including water, that then becomes a potential economic resource as well for that settlement once established, depending on how vigorously human beings are going to work in this new ocean. And so, no, I think the moon is what is it? Somebody, if God wanted us to explore, to go into the solar system, He would give us a moon. Okay. Actually, it also stabilized the Earth, which was probably a good idea as well.
Let's take one more question.
Do you know how many people were on the moon?
How many people are on the moon right now?
We're on the moon.
There have been 12 people go to the moon. Neil Armstrong was the first to step on the moon. I was the 12th. Now, if that's the last question, before anybody gets up, I've got something here that I want the kids to have a chance to get. They're little squeegee moon balls. And so that's going to the kid that just answered the question. Who else? Where? Here we go. Where are we? There you go, kiddo. Don't go away. I got 4 more. Oh, okay. Here we go.
Get over here on the far right. I'm going to sign you up for the Astros next week.
That's it. Thank you.
All right, that was probably the most fun talk we've ever had. So, thank you all for coming, and please join us out in the lobby for reception.
Thank you.